Welcome back. In this section, we're going to talk about one-sided limits, which I briefly alluded to in a previous video. Namely, we've seen before that if we have some function f of x, and this is, say, 2, then the limit as x goes to 2 of f of x doesn't exist. And that's not for want of trying, because if I look at this side of the universe, it really looks like it's going to this point, which we'll say is 2. And if I look at this side of the universe, it really looks like it's going to this point, which we'll say is 5. But the problem is, the left half of the universe and the right half of the universe don't agree on one reality. And so 2 and 5 aren't the same, so this limit just doesn't exist. The idea of a one-sided limit is basically to say, okay, forget the other half of the universe and just look at one side at a time. So if I write down this minus is read as from the left, or from the negative side, whichever way you want to think about it. Okay, so this minus, that's telling me that this is a one-sided limit. That's how you know it's a one-sided limit. That's the title of the section. And so this is saying only look at the left. So just pretend this part of the graph isn't even there, and then say, what's the limit? Well, then the limit is 2. Great. I could do it the other way as well. I took the limit as x goes to 2 from the right of f of x. Now, this is my bling, the plus here. And so this is now saying just look from the right, or just look at the positive side, so pretend now that part doesn't exist. And so I see this nice, beautiful curve, and that's going towards this 5. And so this is 5. And so if you're looking in graphs, one-sided limits give you a way to do just a tiny bit more articulation about what exactly is happening when you have one of these jump discontinuities. That's one piece of what one-sided limits do. Another piece of what one-sided limits do is they let you explain more clearly what's happening at an asymptote. Okay. So if this is our function g of x, okay, and we have our asymptote here, let's say that this is x is 2 again. When we talk about the limit as x goes to 2 of f of x, this still is just undefined. It doesn't exist or whatever. But there's a piece of information that I'm missing with that I might want to know, which is that I might want to know what direction does this arrow point, or what direction does that arrow point. Both of those are reasonable things to want, and we can't express them without, again, using this idea of a one-sided limit. But if I do take a one-sided limit, then I can say the limit as x goes to 2 from the right of g of x, and I can say, what is this running off to? Well, this is running off to the plus infinity on the output axis, while the limit as x goes to 2 from the left of g of x, that's coming from this side, that's running off to the negative infinity on the output axis. And so even if you have one of these asymptotes like this, you might end up with a bunch of different splits, where the right-hand side could be going off to plus infinity and the left-hand side off to minus infinity, like we have here. It could be reversed. This side could be running off to plus infinity and this one to minus infinity. Or it could even be that they both run off to minus infinity or both run off to plus infinity. And one of the benefits of talking about one-sided limits is it lets us talk about that. Here's our good old friend, a piecewise function. remember that this piecewise function is really sort of mooshing together these three functions, and which one of the three functions you get depends on what input you put in. If I want to take some limit involving this sort of piecewise function, I could take something like the limit as x goes to 1 of f of x. Okay. And where is 1? Well, 1 is sort of squarely in the middle of the second line here. Okay. And so this would be the same thing as the limit as x goes to 1 of x squared, which would just be 1. The interesting thing that happens is when you take the limit as x goes to, and then you pick one of the boundaries between these. So for example, the -1 is a boundary and the 2 is a boundary. So the limit as x goes to -1 of f of x, or the limit as x goes to 2 of f of x. I think it's easiest to understand why this ends up being the most interesting if I actually separate this into two questions, namely what happens on the left and what happens on the right. So first of all, let me note that where -1 itself is, that is whether -1 is in the first line or the second line, doesn't actually matter. Because remember, limits don't care about the value at the input you're interested in. So the limit doesn't care about the value at -1. So the fact that -1 is technically in the first line doesn't matter. We only, in this case, care about inputs that are a little less than -1. If I'm at an input that's a little less than -1, then what line am I in? Well, then I'm in line 1. Because numbers that are a little less than -1, they're definitely less than or equal to -1. And so when I calculate this limit, I use the 1 over x version. And so this just ends up being -1, because 1 over -1 is -1. On the other hand, when I look at the limit as x goes to -1 from the right, then I'm now looking at inputs that are a little bigger than -1, and inputs that are a little bigger than -1, those are going to put me in line 2, because numbers that are a little bigger than -1, well, they are in particular bigger than -1. So I'm going to use the second line. And what's going to happen when I put -1 into the second line? I'm going to get +1. And these two answers together tell a story. Namely, they tell me that if I look at the graph of f, and I look at -1, then if I look off to the left, the value ends up doing something where it approaches a value of -1. Whereas if I look at the input -1 coming from the right, then the output ends up doing something where it looks like the value is +1. Okay. In other words, just these two things, the fact that the limit as x goes from -1 from the left and the limit as x goes from -1 to the right are different, tells me again that there is a jump discontinuity of this ugly sort that we've been talking about. In particular, this also tells me that if I take the limit as x goes to -1 of f of x, this thing just doesn't exist. And we can write pretty concisely the reason why now, because the left and right limits disagree. What happens at the other boundary for this function? So that is, what happens at 2? So if I take this limit as x goes to 2 from the left of f of x, and the limit as x goes to 2 from the right of f of x, let's see what these are. So 2 from the left, that's going to put me in line 2. And so when I read this, 2 from the left puts me in line 2. This is going to 2 squared, which is 4. Whereas 2 from the right, now I'm looking at inputs that are a little bigger than 2. That's going to put me in line 3. And so when I look at line 3 now, I'm going to get 2 times 2, which is also 4. And now the fact that these two are the same actually also tells me a story about what the graph of f of x looks like. So if I go to 2, and I go ahead and fill in, let's say this is 4, it tells me that whatever happens over here and whatever happens over here, they match up at this point. So there is no jump discontinuity at 2. In fact, it's continuous at 2. In particular, what does this also mean? This also means that if I take the limit as x goes to 2 of f of x, it does actually work. Namely, it is 4, because the left and the right-hand side both are 4. Okay. And so this is because the left and right limits are equal. That's all for this video. In the next video, we're going to talk about how to algebraically figure out, if you're at one of these spots where there's an asymptote, whether the left is going to plus infinity or minus infinity, and whether the right is going to plus infinity or minus infinity. But that's all for now. I'll see you next time.